Hello, today we're going to be learning that root 2 is irrational. Now, this is a very famous proof which we will cover in its entirety. But before I do that, let me take you on a history lesson on the rich history behind the origins of this amazing proof. Let me introduce you to a group of people known as the Pythagoreans. Now, the Pythagoreans was a cult back in the day that really liked mathematics, so much so that they worship mathematics as they believe that everything in the universe is related to mathematics. However, outside of that, they had very firm beliefs in how mathematics was structured. They only believed that irrational numbers existed, so that means that they believed that all numbers can be either written as an integer or as a ratio of integers, such as 0.333 as a decimal can be written as 1 over 3. They believed that all numbers had this property. You can guess based off their name, the Pythagorean Theorem was one of their favorite formulas, a squared plus b squared equals c squared. Now, if you put side lengths 1 and 1 on the triangle, the hypotenuse of the triangle ends up to be the square root of 2. However, it seemed like the square root of 2 couldn't be written as a ratio of integers no matter how hard you tried. Hippasus is credited as the first person who discovered this, and he thought, maybe there might be another category of numbers that we didn't realize was there before. So he went to the higher mathematicians at the time and proved with certainty that root 2 is irrational. It cannot be written as a ratio of two integers. However, instead of embracing his proof, the higher-ups were very mad and decided that he will pay severely for disrupting the rules of mathematics. From here, we don't know what happened to Hippasus. Legend has it that he was either sent on an island far, far away on a ship, never to return, or he was strapped to a rock and thrown to the bottom of the ocean. And that's the end of the story. There is no happy ending here. Now, poor Hippasus may have died, but his proof did not die. He left behind a very interesting method of proving things in mathematics, and this is going to be what we're going to use to prove that root 2 is irrational. So the method that he left behind is called proof by contradiction. So here is the game plan. To prove that a statement is true, we're going to first assume the opposite is true. So this is just an assumption. Afterwards, we find a contradiction that proves that the original assumption is false. And by doing so, you prove the original statement. Now that was a bit much, but here would be a more detailed example. If we want to prove that A is true, so we want to prove that A is true, and B is the opposite of A, we first assume that B is true. So we're just assuming that B is true. And then we continue assuming B is true, and then we find a contradiction that proves B is false. And by doing so, you have proved A is true. So in terms of proving root 2 is irrational, we're going to assume that root 2 is rational. And then we're going to find a contradiction that proves that it cannot be rational. So therefore it is irrational. Now, some of you may be wondering, why go through all that trouble? You know, if we want to prove that root 2 is irrational, why don't we just prove, root 2 is irrational? Just prove it instead of assuming that it's rational and then disproving it, and then we go back to it being irrational. You would be right, but the thing is, it's very, 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 very hard to prove that root 2 is irrational without proof by contradiction. In math class, some of you may have learned that root 2 goes on and on and on and on and on forever. The only way to prove that root 2 is irrational is to write all the numbers all the way to infinity. And only by doing that, you can prove that root 2 is irrational, which I'm sure many mathematicians didn't have the time to do that. So proof by contradiction might look like we're complicating things, but actually simplifies things. All we have to do is just prove that it's not rational to prove that it's irrational. But anyway, let us officially start with the proof. So let us assume that root 2 is rational. Now, rational means it can be written as a ratio of two integers, and those two integers will be a over b. Now, there are important properties for a and b, so you have to pay very close attention here. So, a property of a is that a is a positive whole number that is greater than 0. What is a positive whole number? It is 1, 2, 3, 4, 5, 6, 7. So just numbers without decimals. That is a whole number. Now, why does it have to be greater than 0? Thing is, root 2 is positive, so a also has to be positive. If a is smaller than 0, then that means we're getting a negative number. We're not getting a negative number. We want a positive number. So a is a positive whole number that is greater than 0. That's the same thing we're also going to assume about b. b is a positive whole number, so 1, 2, 3, 4, 5, any one of those numbers that is greater than 0. So again, because root 2 is positive, this number also has to be positive. Now here's an important assumption. A over b is an irreducible form, which means that you cannot simplify a over b any further. So what is a fraction that is in reducible form? Well, one's like 8 over 16. 8 over 16 can be written as 4 over 8 because you divide both sides by 2. Then you get 2 over 4 and you get 1 over 2. Essentially, you can simplify it further. So also numbers like 3 over 9, you can rewrite it as 1 over 3 by dividing both sides by 3. So essentially, whatever it is, it has to be in simplest form. So such as 2 over 3 or 3 over 4 or 16 over 17, you cannot divide it any further. Now, in order for that to happen, either A or B has to be odd. An important property of all irreducible fractions is that A or B has to be odd. Well, why is that the case? If both A and B is even, then that means you can divide it by 2. And even over an even will never be an irreducible form because you can always divide it by 2. All irreducible fractions always have at least one odd number in them. So, such as 2 over 3, or you can either have the even number on top and the odd number on the bottom, or you can have something like 3 over 4, where you get the odd number on top and then an even number here. Or you can also have an odd over an odd, so you get 1 over 3. That's also odd, and this is also odd. Whatever the case is, cannot be even over even. Okay, now I have to properly define what an even number is and what an odd number is. I'm sure most of you know what an even and an odd number is, but it doesn't hurt to go over it. Even numbers are numbers that can be divided by 2, and you don't get any remainder. Now, it can be rewritten as 2 of a number k. What does that mean? Well, let's say you have 4. 4 can be written as 2 times 2. If you have 8, that is equal to 2 times 4. If you have 16, that is equal to 2 times 8. Or 32 is equal to 2 times 16. So whatever the case is, all even numbers is just 2 times another number that is whole. That is all what it's saying. Okay, let me stretch this here. Odd numbers cannot be divided by 2 to yield another integer. So if you divide an odd number by 2, you're going to get a remainder. That's all. Now that we have all these things, we can finally proceed with the proof. So let us begin. Root 2 is equal to A over B. A over B. Now, we're going to square both sides. So if we square both sides, the square root and the square will cancel out, and we will get 2 is equal to, now, if you remember, when you square a fraction, you square the numerator and you square the denominator. So you get A squared over B squared. Okay, now we're going to multiply both sides by B squared. So these two cancel out. I'm just going to rewrite it as 2b squared is equal to a squared. Okay, now we can make a very interesting observation. The observation is a squared is even. And if a squared is even, that means a is even. Okay, how did I get there? So remember, even numbers can be written as 2 times another number. Right over here, this is 2 times b squared. So b squared is just another number. So 2 times b squared, another number, is equal to a squared. So that means a squared is even. Now, if a squared is even, that means a is also even. Now, how did I get there? Well, 2 squared is equal to 4. 4 squared is equal to 16. 8 squared is equal to 64. Interesting pattern is that when you square an even number, you get an even number. So if a squared is even, we can also deduce that a is also even, because the square of an even number is also even. So we just proved that a is even, just with that. Okay, are you done? Well, not quite, because either a or b has to be odd. A might be even, but b squared could be odd for all we know. So we're not quite done yet, but let us continue. Now, we're going to have to make a substitution here. Because we just proved a is even, a is just 2 times another number. So we can make the substitution a is equal to 2k. Remember, k is just a number. So k is a number. So let's make that substitution. 2b squared is equal to 2k squared. When we're squaring 2k, we square 2 and we square k. So we end up getting 2b squared is equal to 4 times k squared. Okay, and now let's divide both sides by 2. So this will cancel out and this will become 2. And we get b squared is equal to 2k squared. Now, we can make another interesting observation here. B squared is even. Why is it even? Because b squared is 2 times another number, which we just defined earlier, that an even number, just like with a, 2 times another number makes it even. So that means b squared is even. And if b squared is even, that means b is also even, because an even number squared will always equal an even. So just exactly like before, we just proved b is even. And here we have our contradiction. So this is exciting. We just got our contradiction. What was our contradiction? Well, we just said here, either A or B has to be odd. Either A or B has to be odd. That was a condition. But we just proved that A is even and that B is also even. And if those two are even and one of them has to be odd, that means our original assumption was false. So at long last we prove root 2 cannot be rational, therefore it is irrational. And that is how we prove that root 2 is irrational. And that is all. I hope you learned something from this video, and this is Low Academy signing off.